Hi, there's much talk about hydrogen being the fuel of the future. The element is, after all, the fuel of the stars, and by far away is the most abundant element in the universe. Helium is the next most prevalent, and together they amount to about 97% of the total abundance of all elements. But in our present discussion, it is hydrogen gas, H2, which is the key. There is very little of it in the atmosphere, and on Earth's surface layers, really the element exists largely as water, H2O. The appeal of hydrogen as a fuel is in its cleanliness. Two molecules of H2 react with one of oxygen gas, O2, to form two molecules of water, H2O, and a lot of energy. But we need to make the H2 gas, and generally that is from the reaction of a carbon source with water and sometimes with some oxygen. If the carbon source is black coal, then the hydrogen gas so-called has been labelled black hydrogen. If it is from brown coal, lignite, then it is labelled as brown hydrogen. If natural gas is predominantly methane and is the carbon source, this is labelled as grey hydrogen. As well as H2 gas, which is the same whichever source it comes from, there are byproducts of the oxides of carbon, mostly CO2. The ways to make this a low-carbon fuel are either as blue hydrogen or as green hydrogen. Blue hydrogen requires extra steps in production, say from black or grey hydrogen, which extracts the CO2 and stores it. That's carbon capture and storage, called CCS. And we look at this in another video. Both steps do have plants being tested. Green hydrogen is completely different. Generally, water is the source. It is the reverse of the burning of hydrogen, and it needs a large input of energy, either as light or electricity. And to be green, that energy has to be produced using a sustainable source. From the figures available in 2018, the production of hydrogen amounted to nearly 120 million tonnes, and much of it was as a byproduct, most commonly of the production of chlorine gas by electrolysis. About 800,000 tonnes only was produced by green or blue routes. The majority of hydrogen produced is used for chemical production. Much is used to make ammonia, largely for fertilizer, and another significant proportion is in the petrochemical industry, and specific organics like methanol, and from that acetic acid. There is relatively little for energy production at all. By comparison, here is the energy used in that same year, billions of tonnes of oil equivalent per year. Use of hydrogen in transport is estimated to have been under 10,000 tonnes per year. So to convert all of these demands into a supply of sustainable hydrogen production is a very steep climb indeed. In terms of transport, hydrogen does have some advantages over a lithium-ion battery as it is at present. The energy density in megajoules per kilogram is vastly higher. For a battery, it's only about 2/3 of a megajoules per kilogram, but for hydrogen it is over 140. But in terms of volume, H2 has to be pressurised to have a higher energy density, and a pressure of about 700 atmospheres is often quoted. Then the energy density per volume is about double that of some lithium-ion batteries, but that needs a weighty cylinder to store safely. The emissions of CO2 per sector in 2010 were much as you might have expected, with energy generation the largest and transport the second largest. So how can hydrogen contribute to transport? A study reported in 2018, studied by Transport and Environment from Brussels, provided the following comparisons for a sustainable car. In principle, the clean hydrocarbon fuel could be generated on the vehicle by firstly electrolysis of water to give hydrogen, secondly by capturing CO2, and thirdly, conventional fuel can be generated by what is called a Fischer-Tropsch synthesis. The car is then driven by an internal combustion engine. The overall energy efficiency was estimated to be only about 13% in such a vehicle. But if instead the hydrogen is converted into electricity by a fuel cell, then there is a gain because of the much higher efficiency of electric motors. The overall efficiency is then about 2.5 times larger, or about 30% in total. Alternatively, using a rechargeable battery, the energy efficiency of the car is another factor of 2.5 times higher, about 77%. The hydrogen-powered vehicle would be favoured for large vehicles with long ranges, where the higher energy storage of hydrogen can win out. Examples might be diesel buses, trucks and trains. And since the motor is an electric one there should be no emission of NOx. Volatile organics and particulates also are lost, and as a result there would be an improvement of air quality and loss of ozone production in the troposphere. There are potential applications of hydrogen as a fuel that can be greener once the appropriate means of manufacture have been expanded. This will be all the faster if the overall energy demand is reduced by more efficient heating and travel and doing less. As an example, there are developments envisaged at the port of Rotterdam. Green hydrogen is planned to be made by electrolysis using energy from wind power. Blue hydrogen would involve cleaning up the hydrogen from natural gas and refinery gases and by carbon capture and storage into the depleted gas fields under the North Sea. And that is an interesting development in the future.